And unlike the sum and difference rule, where it sure would be nice if you could just do the derivative of the first one and times it by the derivative of the second one, that does not work. Because the gut feeling is, oh, wouldn't it be nice if the first one's derivative is just 3x squared plus 3, second one's derivative 2x minus 5, and I just multiply those together? That would sure be nice, but it doesn't actually work. Okay. And if you guess that, put yourself in good company, because Leibniz also guessed that his first try and found out that it didn't work. But he ended up inventing calculus on his own, so don't feel bad if you guess something. That is a lot of what mathematicians do. They make a hypothesis, and they try a bunch of examples. And if it keeps working with their examples, then they say, maybe I'm going to try and prove this works for everything. And so on Monday, they go to the work and they found a bunch of examples that work, and they try to prove it works for everything. And if they fail to prove it works for everything on Monday, on Tuesday, they go into work and try to find an example that doesn't work. And they spend all Tuesday trying to find one that doesn't work. And if they can't find one all Tuesday that doesn't work, Wednesday they go back to work and they try to prove that it works for everything again. And they go back and forth between trying to find an example that doesn't work, because then you can, if you just find one example that doesn't work, you can throw it out the window and say, I don't have to worry about proving it anymore, because one example shows that it can't be proven. But if you can't find that one example that drives you crazy, there must be a way to show that it always works. Yes?
Can't it be that it works under special conditions? Then at least you have a rule which applies.
Right, and if you say, these are my special conditions, and then you prove it, right? And then, I mean, there's all sorts of examples. Like there's a quadratic formula, right? Quadratic formula lets you solve all quadratics. There's a quintic formula. I mean, a cubic formula. It is very ugly. It's huge, okay? But then you start to say, well, if I had an x to the 4 or an x to the 5 equation, shouldn't there be a formula that lets me solve those ones? But that ends up being more and more complicated. And then they've proven that you can't have formulas after a certain power. But that took a long time to do those kind of things. Anyways, we're getting into complicated proofs. Right now, here's a simpler example. If your functions were, this is how you could prove that this does not work. If my first function, I will call that my function u, and my second function, my function v. If I thought it was u prime times v prime, well, the derivative of this would be 1, right? This is our guess, trying this hypothesis. The derivative of u would be 1. The derivative of x to the 4 would be 4x cubed, and that is just 4x cubed. But of course, we know we can simplify this with our rules. It's actually the same as y equals x to the 5. And that derivative we know to be 5x to the 4. And since these two do not match, we know that this isn't the correct rule. So what we do is we play around with a lot of equations. We manipulate those equations algebraically, and we start looking for more patterns. And eventually, you come up with this rule. That does work all the time. Now I'm going to use some color coding so that you can see what's happening here. We have our original function. Our original function is made up of two functions that are multiplied by each other. The derivative then becomes, keep the first function the same, and then multiply by the derivative of the second function. Then keep the second function the same and multiply by the derivative of the first one. And it doesn't matter the order. So basically, keep one the same and multiply it by the derivative of the other one, and then add the opposite of that, keep the other one the same, and multiply by the derivative. Yes? Why this happens? No. So what we're going to do in this course, again, look in your textbook. I believe and there's proofs online. So how does one come to this proof? Again, the idea, like I was saying before, you would look for patterns, and you'd start noticing this pattern, and then once you notice that pattern, then you try to prove that pattern. But this is hard to do because you have to imagine, right, any function. This is true no matter what function we put in for yellow and what function, as ugly as you can imagine. This function could be sine of bracket x cubed plus 5x squared plus 7x times cos of bracket 7x cubed plus the natural log of x inside of sine. And this will still work. It's a very powerful rule because we're saying it works for any function we can imagine. Now this is one set of notations. If we use Leibniz's notation, we can do the same thing. Instead of writing u of x, we just have a u there for that function. And instead of writing v of x, you could just have v there. And the same idea happens. We take our first function and then multiply by the derivative of the second function plus our second function multiplied by the derivative of the first function. So when I write du dx, that means I'm taking the derivative of the function with the u. When I write dv dx, I'm taking the derivative of the function with the v. And dy dx is the derivative of the whole thing. We're going to do this one with our new rule, and we're going to do this one using our old technique. So I'm going to draw a line down the middle here. In one way, I'm going to think of this. Here's where the multiplication is. Again, I'm going to color code u with yellow, that's u, and v with green, that would be all of this. So dy dx would equal u times by the derivative of the second one. That's just 2. Derivative of 2x minus 1 would just be 2. Plus the second one multiplied by the derivative of the first one, and the derivative of the first one is 2x squared. Again, color coding how we started off. This stayed the same, times by the derivative of the second one, plus this stayed the same as before, times by the derivative of the first one. Yes, it's just 2x, thank you. Whoa. And now you could expand this and simplify and have like terms put together. However, it's generally accepted unless you're wanting to use this later on for some simplifications. For the most part, you'll be able to leave it like this to show that you really understand. Your textbook, however, in its answers always expands and simplifies things and factors. So you'll get your answer, and then please take the time to try and see if you can get the same answer they have in the back of the book, because that's really where you're going to improve your algebra skills in those kind of manipulations. Now, we didn't need the product rule for this one. Can you see that you could expand this by multiplying the x squared through? In fact, 2x cubed minus x squared, that's not hard to do. and then getting the derivative is really quick and simple that way too. Which one do I like better? I like the one on the right better because it gets a simplified answer quicker and is more elegant looking in its solution. That's an opinion. Maybe you really like highlighters, and the one on the left allows you to use more highlighters because you like to color code things. So then that's a better solution for you. That's fine.